Hello and welcome to this quick review of the concept of lattice enthalpy and Born-Haber cycles. What we're going to look at in general is an application of Hess's law to the formation of an ionic lattice, and the type of cycle that you draw at second year level is called a Born-Haber cycle. There's lots of different processes involved in this, so they have to come in a certain order for the overall process to make sense. And before you go any further, it's really important to have some flashcards ready so that the rest of the video clip will make sense. The first one is standard enthalpy change of formation, and the symbol is included there as well. Then you've got standard enthalpy change of atomization. Then there's one that might be quite familiar to you from your first year, first ionization energy. Up next is first electron affinity. And finally, we have what's called lattice enthalpy. So although I'm not going to go through the individual definitions of each of these, there are some things that they have in common. Firstly, they're usually applied to 1 mole of substance or 1 mole of species, and the species usually are in gaseous form unless the definition states otherwise. So, for example, the standard enthalpy change of formation requires that all reactants and products are in their standard states. So it's worth pausing the clip at this point and looking up all these definitions and make a flashcard for each one. Then you can come back, and I'll assume that throughout the rest of the clip you'll have your flashcards for the definitions in front of you. So earlier we mentioned Hess's law. It might be worth just remembering what Hess's law tells us. So when you first learn about Hess's law at A level, generally it's applied to fairly simple organic reactions. So there's nothing to stop you taking that a step further and applying the same idea to inorganic reactions, such as the formation of an ionic lattice, for example. So if we consider the difference between a solid ionic lattice and the elements in its standard states, if you take your flashcard for the enthalpy change or standard enthalpy change of formation, it's fairly obvious that it's going to take you from the elements in their standard states to a solid ionic lattice. Now, because it's an exothermic process, it's a decrease in energy. Why is this an exothermic process? This is because ionic bonds are being made. And notice the arrow actually touches both of the lines. If anything, the arrow's gone down slightly too low. So if you look where the arrow points, I'm just going to slightly correct that, like so. Okay, so the next thing to consider is the formation of gaseous atoms. This process is called the standard enthalpy of atomization. Now here it's an endothermic process because the energy arrow points up, and this is because bonds are being broken to separate the atoms out into gaseous form. So the next process is ionization energy, which turns the gaseous atoms into gaseous ions. This should link up with the definition you've learned from your first year, and you may have your flashcard in front of you to remind you of this. Electrons being removed from atoms requires energy, so therefore the arrow points up again. And it's also worth remembering that depending on the ions that you're forming, there may be more than one ionization happening at this stage. And if you check your definition, you'll see that it's only positive ions being formed at this stage, not negative ones. That's taken care of in the next process. So remember, at the very top you've only got the gaseous positive ions. So to get to the stage where you've got positive and negative gaseous ions, you need to make sure that the non-metal atoms gain electrons at this point as well. So this is called the electron affinity. So finally we're able to put in the lattice enthalpy. So this diagram is now called a Born-Haber cycle. So it represents the different routes that can be taken when we form a lattice. So some of these will be pieces of data that you'll be given in a table, for example, in a question, and some of them might be ones that you're not given. So generally what happens is one of them you're not given, and you have to work out the rest. Sorry, one of them you're not given, and you have to use the rest to work it out. So let's look at an example that you might see in a textbook. So this is the Born-Haber cycle for the formation of the lattice for cesium chloride, CsCl. And you can see quite clearly that you've got all of the different parts of it apart from the lattice enthalpy itself. So the way to read this is to look at where you start and find the indirect route. So the direct route is unknown, so obviously we have to use the Born-Haber cycle to work it out via the indirect route. So you can see where we start and see where we finish. So the easy thing to do is just to follow the arrows around. So the thing to remember is if the route's direction travels against an arrow, you simply reverse the sign. So let's have a look at how we might do this. So working my way round from where it says start to where it says finish, but travelling in an anti-clockwise manner, in other words, following that red arrow, I now need to label each of my enthalpy changes to make sure I know what particular substance or species I'm referring to. So now we know what all of these different expressions mean, we can also label the lattice enthalpy that we're trying to work out. So grab a pencil and some paper and see if you can work it out. You'll need your calculator to imagine as well. And then resume the clip to see if we're in agreement when I will provide the answer. So by adding up all of the values, but bearing in mind that if the arrow the direction you're travelling in goes against the direction of the arrow, you reverse the sign. So if we apply that idea to every single value, you can see that the signs have been reversed accordingly, and that gives us minus 663 kilojoules per mole, because we've applied the Hess's law idea of taking an indirect route. So starting at the top and working around anti-clockwise down to the finish. So this is another one. It's completed already, and there's several sort of differences between this one and the one we saw before. So let's now look at a couple of special cases that sometimes come up. In this particular example, the negative ion is a 2- ion. So, for example, the O- has to gain an electron to become O2-. So that means repulsion has to be overcome, so we have an endothermic process requiring energy. In this example, the positively charged ion is calcium 2+. So to match that, you've got to actually ionize calcium twice. In other words, go from Ca to Ca+, and then from Ca+ to Ca2+. So for Ca2+, you've got to atomize chlorine twice as well. So you have to multiply the atomization up accordingly. Now, these two types of examples come up quite a lot, so it's worth looking out for them. So the lattice enthalpy idea is most commonly applied in A-level to the enthalpy change of solution when an ionic solid dissolves. So the enthalpy of solution actually has two things that have to happen before it actually takes place. So the first thing is that all the attraction between oppositely charged ions are overcome. So the hydration process is where each individual ion is surrounded by polar water molecules to form something called a hydration shell. So the water will orientate itself so the appropriate partial charge on the H2O molecule will attract to the surface of the ion of opposite charge. So the oxygen atoms in water molecules are partially negative, so they'll attract to positive cations. The hydrogen atoms are partially positive, so therefore will attract to negative anions. So if we take sodium chloride, for example, if we take a sodium ion, what's going to happen is that the partially negative oxygen will attract to its surface. So this is an exothermic process. Obviously, with a chloride ion, you would have water attracting via the H atoms. So this is also an exothermic process. So therefore, the enthalpy of hydration tends to be exothermic. So the greater the hydration enthalpy, the stronger the attraction between water and the ion. So the smaller your ionic radius, the more exothermic the hydration enthalpy will be. So you can see that with this quick comparison of the halide ions. Obviously the fluoride ion has a very, very small ionic radius, so its enthalpy of hydration is much more exothermic than, for example, the iodide ion. So how would all this fit into a Born-Haber cycle? So here's a Born-Haber cycle for the enthalpy of solution of potassium chloride. Have a look at the lattice enthalpy and see what direction it points. Then have a look at what we've said about what has to happen. All the attractions between the oppositely charged ions are overcome. Now if you look at your flashcard for the definition of lattice enthalpy, it's for the formation of 1 mole of lattice. So therefore, what we really need to do is to slightly adjust our equation near the top of the page. So because the lattice enthalpy is defined in terms of the formation of the lattice, we have to do the opposite. So we apply the minus sign to the lattice enthalpy value. So it might be worth pausing the clip and using the hydration solution data for KCl to see if you can calculate its lattice enthalpy. So start at the top, work your way down and see what you end up with. So looking at the values, that should give us minus 711 kilojoules per mole. So the next thing to do is to look at what affects the enthalpy change of solution overall, because it's a combination of hydration and lattice enthalpy being overcome. So looking at the charge on the cation first, the greater the charge, the more exothermic the hydration enthalpy. And the reason for that is the stronger the attraction between the ion, the positive ion, and the negative, the delta negative part of the water molecule. And as the size of the ion decreases, the hydration enthalpy also becomes more exothermic. So as the size of the ion decreases and you get a greater charge, you get a stronger attraction between the ion and the water molecule. So both those two things together mean that you get a more exothermic hydration enthalpy. Now, if you get a stronger attraction between oppositely charged ions in the lattice, you have a more endothermic lattice enthalpy to overcome, because you've got to break the lattice up to dissolve the solid. So the enthalpy of solution is a very fine balance between the magnitude of these two factors, one being an exothermic process and one being an endothermic process. Remember, exothermic processes involve attractions, endothermic processes involve bonds being broken or attractions being overcome. So hopefully this little clip's provided a useful introduction to, first of all, how we use Born-Haber cycles, secondly what lattice enthalpy is, and thirdly how we apply lattice enthalpy in hydration to working out enthalpy of solution. So thanks for listening, and until next time, see you soon.